Introduction. Today, we will study the classification of elements. Okay, teacher, but how do we classify the elements? We will classify the elements with the help of periodic table. Teacher, what is periodic table? Periodic table is the arrangement of elements in such a way that similar elements fall in a group, whereas dissimilar elements are separated. So, teacher, we will classify the elements on the basis of their properties? Well said. Thank you, teacher. So, let's proceed. In this lesson, you will study the elements that are known and classify them. Objectives. At the end of this lesson, you will be able to classify the elements in periodic table, discuss genesis of periodic classification, explain Mendeleev's periodic table, state modern periodic law, know the nomenclature of elements with atomic number greater than 100, discuss the electronic configurations of elements, classify the periodic table into S, P, D and F block, explain periodic trends in properties of elements, explain periodic trends in chemical properties. Why do we need to classify elements? Before the beginning of 18th century, few elements were known. As the time passes, large number of elements is known, and today we know 114 elements, and now it becomes quite essential to classify them. The classification of elements led to the formation of periodic table. Thus, periodic table may be defined as the table giving the arrangement of all the known elements according to their properties, so that similar elements fall within the same vertical column and dissimilar elements are separated. Genesis of periodic classification. Daubigny's triads. He observed that certain similar elements exist in group of 3 elements, which he named triads. An interesting feature of these triads is that the atomic mass of middle member was the arithmetic mean of the atomic masses of the other 2 members of the triad. For example, lithium, sodium and potassium constitute one triad. Atomic mass of sodium is equal to atomic mass of lithium plus atomic mass of potassium is equal to 7 plus 39 by 2 is equal to 23. However, this concept of triads could be applied only to a limited number of elements. Law of octaves. J. A. Newlands arranged the elements in the order of increasing atomic masses and noticed that the 8th element starting from a given one is a kind of repetition of the first. The following arrangement illustrates the law of octaves. The law of octaves could not be applied beyond calcium. Moreover, with the discovery of noble gases, the 8th element no longer remains a similar element. Mendeleev's periodic table. Mendeleev gave a periodic law which states that the properties of elements are the periodic function of their atomic masses. Uses of Mendeleev's periodic table. Number 1. In periodic table, elements are classified into groups with similar properties, thus facilitating the study of properties of elements. Number 2. Mendeleev left certain vacant places in his table, which provided a clue for the discovery of new element. Some of the properties could be predicted with a fair accuracy. For example, both gallium and germanium were not discovered at the time when Mendeleev proposed his periodic table. Mendeleev named these elements as XI-aluminum and XI-silicon respectively. Number 3. With the help of this table, doubtful atomic masses of certain elements were corrected. Modern periodic law and the present form of the periodic table. The modern periodic law states that the physical and chemical properties of the elements are the periodic function of their atomic number. The present form of the periodic table is the long form. A horizontal row of a periodic table is called a period. A period consists of a series of elements having same valency shell. There are 7 periods in all, which are numbered as 1, 2, 3, 4, 5, 6 and 7. Periods 2 and 3 contains 8 elements each and are called short periods. There are 18 elements each in 4th and 5th periods, and they are called long periods. 6th period, containing 32 elements, is called the longest period. A vertical column of the periodic table is called a group. Elements belonging to the same group are said to constitute a family. For example, elements of group 17 constitute halogen family. Similarly, elements of group 16 constitute oxygen family. Nomenclature of elements with atomic numbers greater than 100. It was decided by IUPAC, International Union of Pure and Applied Chemistry, that a systematic nomenclature be derived directly from the atomic number of the element using the numerical roots for 0 and numbers 1 to 9. The name for various digits of the atomic number are written together in the order of which makes the atomic number, and IUM is added at the end. Example: the element with atomic number 120 has not been discovered. What would be the name and symbol of this element? Solution: the given atomic number is 120. So, from the table given for 120, we can write unbinyl. After this, we add IUM to this name, so it becomes unbinylium, and its symbol is UBN. Electronic configurations of elements and the periodic table. The arrangement of electrons in the orbitals of an atom is called electronic configuration. The number of the period represents the principal quantum number of the valency shell of elements present in it. Electronic configurations in periods. The first period corresponds to the filling of electrons in first energy shell, that is, n is equal to 1. Now, this energy levels has only one orbital, that is 1s, and therefore it can accommodate 2 electrons. This means that there can be only 2 elements in the first period. The second period starts with the electrons beginning to enter the second energy shell, that is, n is equal to 2. There are only 4 orbitals, that are 1 2s and 3 2p orbitals to be filled, which can accommodate 8 electrons. Thus, second period has 8 elements in it. In the third period, that is, n is equal to 3, electrons added into 3s orbitals. So, successive filling of electrons into 3s and 3p orbitals makes third period. The fourth period corresponds to n is equal to 4. It starts with the filling of 4s orbitals. However, after the 4s but before the 4p orbitals, there are 5 3d orbitals also to be filled. Thus, in all, 9 orbitals, 1 4s, 5 3d and 3 4p have to be filled. It may be noted that the filling of 3d orbitals starts from scandium atomic number is equal to 21. The elements from scandium atomic number is equal to 21 to zinc atomic number is equal to 30 are called 3d transition series. The fifth period beginning with 5s orbital, that is, n is equal to 5, is similar to fourth period. There are 9 orbitals, 1 5s, 5 4d and 3 5p to be filled, and therefore there are 18 elements in fifth period as well. The sixth period starts with the filling of 6s orbital, that is, n is equal to 6. There are 16 orbitals, 1 6s, 7 4f, 5 5d and 3 6p, in which filling of electrons take place before the next energy level starts. The filling up of 4f orbitals begins with cerium atomic number is equal to 58 and ends at lutetium atomic number is equal to 71. It constitutes the first F transition series, which is called lanthanide series. The seventh period begins with 7s orbital, that is, n is equal to 7. It corresponds to the filling of 7s, 5f, 6d and 7p orbitals, but it is still incomplete. At present, there are only 19 elements in it. The filling up of 5f orbitals begins with thorium atomic number is equal to 90 and ends up at lawrencium atomic number is equal to 103. It constitutes second F transition series, which is called actinide series. Group-wise electronic configuration. Elements in a group exhibit similar chemical behavior because they have similar electron distribution in their outermost orbitals. Electronic configurations and types of elements. S, P, D, F blocks. The long form of periodic table can be divided into four main blocks. These are S, P, D and F blocks. There are two exceptions to this categorization. First is helium, which belongs to S block elements, but it is placed in P block elements because its outermost shell is completely filled, that is 1s2. Second is hydrogen, as it has single electron, so it can be placed in S block, and it can also gain an electron and behaves as the elements in group 17. So, due to this, it is placed at the top of periodic table. The S block elements. The elements in which the last electron enters the S subshell of their outermost energy level are called S block elements. This block is situated at extreme left of the periodic table. It contains elements of group 1 and 2. Their general configuration is where N represents the outermost shell. The elements of group 1 are called alkali metals, whereas the elements of group 2 are called alkaline earth metals. The P block elements. The elements in which the last electron enters the P subshell of their outermost energy level are called P block elements. The exception is helium. The general configuration of their outermost shell is Group 18 contains noble gases and their electronic configuration is the elements of group 17 are called halogens and the elements of group 16 are called chalcogen. They readily gain an electron to attain stable configuration. The D block elements, transition elements. The D block elements are the elements with electronic configurations in which the d orbitals are being partially filled. Their general electronic configuration is. General characteristics of D block elements are they form colored complexes. Most of them exhibit paramagnetism. Most of them possess catalytic properties. They form alloy. For example, brass is an alloy of copper and zinc. The F block elements. Inner transition elements. The F block consists of two rows of elements at the bottom of the periodic table called as lanthanoids and actinoids. Their general electronic configuration is where N represents the outermost shell. They consist of two series of elements placed at the bottom. The first series follow lanthanum and are called lanthanoids, whereas second series follow actinium and are called actinoids. General characteristics of F block elements are they show variable oxidation states. They are high melting metals. They have high densities. Most of the elements of actinide series are radioactive. Metals, nonmetals and metalloids. Metals. Metals are strong. Metals are malleable and ductile. Metals have high melting and boiling point. Metals are good conductors of heat and electricity. Metals shine on polishing. Non-metals. Non-metals are brittle. Non-metals are poor conductors of heat and electricity. The elements which show the property of both metals and non-metals are termed as metalloids. Periodic trends in properties of elements. Trends in physical properties. A. Atomic radius. Atomic radius is defined as the distance from the center of nucleus of the atom to the outermost shell of electrons. It is not possible to find precisely the radius of the atoms because of the following reasons. Atom is too small to be isolated. The probability distribution of an atom is affected by the other atoms present in its neighborhood. Size of an atom also changes from one bonding state to another. If the two atoms are bound by a single bond in a covalent molecule, then we measure. Covalent radius is defined as 1/2 of the distance between the centers of the nuclei of two similar atoms bonded by a single covalent bond. For metals, we measure metallic or crystal radius. It can be defined as half of the internuclear distance between two adjacent atoms in the metallic lattice. The metallic radius of an atom is always larger than its covalent radius because metallic bond is weaker than covalent bond. B. Ionic radius. Ions are formed when the neutral atoms lose or gain electrons. Loss of electron results in cation, whereas gain of an electron results in anion. Ionic radius may be defined as the effective distance from the nucleus of the ion to the point up to which it has an influence in the ionic bond. Important points. The radius of cation is smaller than that of the parent atom. The radius of anion is larger than that of parent atom. The ions having same number of electrons but different magnitude of nuclear charge are called isoelectronic ions. For example, the size of these ions are in the order. Ionization enthalpy. Ionization enthalpy may be defined as the amount of energy required to remove the most loosely bound electron from the isolated gaseous atom. If we provide ionization energy to the gaseous atom A, it loses an electron. Successive ionization energy. Once the first electron has been removed from the gaseous atom, it is possible to remove second and successive electrons from positive ions one after the other. For example, the amount of energy is required to remove most loosely bound electrons from unipositive, dipositive, tripositive ions of the element in gaseous state are called second, third, fourth ionization energies respectively. It may be noted that ionization energy 3 is greater than, ionization energy 2 is greater than, ionization energy 1. The ionization energy depends upon the following factors. Size of the atom. As the size of the atom increases, the outermost electrons are less tightly held by the nucleus. As a result, it becomes easier to remove electron. Therefore, ionization energy decreases with increase in atomic size. Magnitude of nuclear charge. With the increase in nuclear charge, it becomes more difficult to remove an electron and therefore ionization energy increases. Screening effect. In multi-electron atoms, the electrons present in the outermost shell do not experience the complete nuclear charge because of repulsive interaction of the intervening electrons. Thus, the outermost electrons are shielded or screened from the nucleus by the inner electrons. This is known as screening effect. An increase in the number of inner electrons tends to decrease the ionization energy. Electronic configuration. The atom having a more stable configuration has less tendency to lose the electron and consequently has high value of ionization energy. Electron gain enthalpy. Electron gain enthalpy may be defined as a measure of the ability of an atom or molecule to form a negative ion, expressed as the energy released when an electron is attached. The process can be expressed as: the process can be exothermic or endothermic. Factors affecting electron gain enthalpy. Nuclear charge. Greater the magnitude of nuclear charge, greater will be attraction for the incoming electron, so that larger will be the negative value of electron gain enthalpy. Atomic size. If the size of the atom is large is the distance between nucleus and additional electron, and smaller will be the negative value of electron gain enthalpy. Electronic configuration. If the atom has stable configuration, then lesser is its tendency to accept the electron, and larger will be the positive value of electron gain enthalpy. Electronegativity. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. The factors on which electronegativity depends are: effective nuclear charge, atomic radius. Greater the effective nuclear charge, greater is the electronegativity. Smaller the atomic radius, greater is the electronegativity. The most electronegative element is fluorine. Periodic trends in chemical properties. Periodicity of valency or oxidation states. The valency of an atom is the number of electrons present in the outermost shell. The number of valency electrons increases from 1 to 8 on moving across a period. The valency to the elements with respect to the hydrogen. On moving down a group, the number of valency electrons remains same, and therefore all the elements in a group exhibit same valency. Anomalous properties of second period elements. The elements in the second group show many properties which are not of their group. For example, compounds of beryllium and lithium show a degree of covalency which is not found in the other S block elements. Nitrogen and oxygen form diatomic molecule, whereas other members of their group form polyatomic molecule. Diagonal relationships. The electronegativity of lithium, beryllium and boron leads to diagonal relationships. Lithium is strikingly similar to magnesium, beryllium to aluminum, and boron to silicon. Electronegativity increases from left to right across a period. Periodic trends and chemical reactivity. The chemical reactivity among alkali metals is by the loss of an electron and forms cation, whereas halogens also show reactivity nature by the gain of one electron and forms anion. The chemical reactivity is lowest at the center of the periodic table. Assessment. Before proceeding further, let us know how much have you learned. Drag and drop the correct option. Did you know? On May 31, 2012, the International Union of Pure and Applied Chemistry IUPAC approved the addition of flerovium and livermorium to the periodic table of elements. Summary. Let us summarize what we have learnt. At present, 114 elements are known. Daubigniers observed that certain similar elements exist in group of 3 elements, which he named triads. J. A. Newlands arranged the elements in the order of increasing atomic masses and noticed that the 8th element starting from a given one is a kind of repetition of the first. Mendeleev gave a periodic law which states that the properties of elements are the periodic function of their atomic masses. The present form of the periodic table is the long form. The periodic table can be classified into 4 blocks, that is S, P, D and F block. The valency of an element is the number of electrons present in the outermost shell. The elements in the second group show many properties which are not of their group. This is called as anomalous properties of second period elements. The electronegativity of lithium, beryllium and boron leads to diagonal relationships.